Hey there guys, how's it going? This is Mike coming back at you with another video on number theory. In the previous video, we saw binary and decimal representation of numbers. We saw how to write some numbers in binary, and then we learned about the test for divisibility by 11. In this video, we are going to start a very important topic in this chapter, as well as in the whole course. This is a very important type of problem that you will need to know how to solve. These types of problems will be showing up not only in this video, but for a few videos afterwards. They make for very good quiz or test questions, so you definitely want to pay attention. You definitely want to know how to solve these equations, which are linear congruences. A linear congruence is an equation of the form AX is congruent to B mod N. And what a solution to this thing is any integer x which makes the above congruence true. Now, looking at AX is congruent to B mod N, and looking at what that's saying in terms of divisibility, we said that A is congruent to B mod N if N divides A minus B. So AX is congruent to B mod N means that N divides AX minus B, which, going back to chapter 2, we know that in terms of divisibility, that means that AX minus B has to equal N times some whole number Y. Now, if I switch places of the B and the NY, I get AX minus NY is equal to B. And looking at this thing here, in terms of X and Y, what we actually have here is a linear Diophantine equation. Now, you may be thinking, okay, it's AX, but then it's plus BY equals C. Well, we could just take this minus N here and give that some new name, plus capital B, and then I could take this guy here and give it a new name, say capital C. And there we would have our linear Diophantine equation. So we're going to pull all those tools, we're going to pull all those rules and properties out of our memory banks, all those things for solving linear Diophantine equations. We're going to use those things here. Now, before we go about solving these things, the big questions we have to answer first are, 1, does the linear congruence even have integer solutions? Because this is a course on number theory, we're focusing on whole numbers, so we want solutions that are whole numbers. So first question is, do we have integer solutions? And then follow-up question number 2, if we do have integer solutions, how many do we have? Well, to clarify on the how many solutions do we have, technically, if we have integer solutions, technically we have an infinite number of them, but because we're dealing with congruences, an infinite number of solutions can all be congruent to each other. Here's a really basic one here. 3x is congruent to 12 mod 19. It's really straightforward to see that if I plug 4 in for x, I'm going to get 12 is congruent to 12 mod 19. So 4 is one solution. Well, you can try 23, you can try 42, try 61. If you plug all of those guys in for x, this linear congruence holds. You can also do minus 15, minus 34, minus 53, minus 72, and all of those are going to be making this linear congruence true as well. But the problem is, those are all solutions that are mutually congruent to each other. And we say that they're mutually congruent to each other because we're adding to each one what our n value is. We're just adding 19 onto each of those numbers, so that when we take those mod 19, they would all come down to the same number of 4. So we say, for our purposes, that these are really all the same one answer. Yes, technically they are different numbers written out, but when solving a linear congruence, these things are really all the same thing. They're part of what's known as an equivalence class. So when we talk about the number of solutions, we're talking about the number of mutually incongruent solutions to a linear congruence. We're talking about how many solutions how many solutions do you have to the given linear congruence that you can't obtain by just adding your n value onto one solution that you find. So the criteria for if you have integer solutions, and if so, how many, is very simple. The linear congruence, AX is congruent to B mod n, has a solution if and only if D divides B, where D is the GCD of A and n. So you're going to take your A value, take your n value, find the GCD of those two numbers. If that GCD is a factor of B, then you have integer solutions. If it doesn't, you do not have integer solutions, and we stop right there. Now, if we do have integer solutions, so if D does divide B, then there are D mutually incongruent solutions to the given linear congruence. And before we see how we're going to solve these guys, we're going to remind ourselves of a very handy result that we are going to be using. If A is congruent to B mod n, and D divides A, D divides B, and D divides n, then A over D is congruent to B over D mod n over D. And as I said, we're going to be using this guy quite a bit. We're going to be using this guy in just about every linear congruence that we solve. There are two ways that we can solve these guys. You can use the Euclidean algorithm. Given the stage of the course that we're in, that may be a more surefire, a more concrete way to come up with the correct answer. But overall, it is more time consuming. Any problem that you'll see from me in this course, we can use congruence properties to solve these guys, and it will go by a lot quicker, but you have to make sure that you follow the steps that I point out. You have to follow those very, very closely, because if you don't follow them, things will get messed up, and then you will, in all likeliness, not come up with the correct answer. Okay, so this is how we're going to solve these linear congruences using congruence properties. We're going to solve the linear congruence 18x is congruent to 30 mod 42. First thing we always have to do, check to make sure that the GCD of your A value and your n value divides your B value. So the GCD of 18 and 42, really not too bad to find out that that is 6. And 6 does divide 30. Make it very clear that that is a 6. So we do have integer solutions. And then we also know that the number of mutually incongruent solutions we have is this GCD. So 6 mutually incongruent solutions going on here. There we go. 6 mutually incongruent solutions to this particular linear congruence. First thing you're always going to do is you're going to take every number in your congruence, your A, your B, and your n value, and you're going to divide every one of those numbers by that GCD. So 18 divided by 6, 30 divided by 6, and 42 divided by 6. And that's going to give us 3x is congruent to 5 mod 7. And pay special attention and note that value. That n value that we were given to start with divided by our GCD, because we're going to be coming back to that guy at the end of this problem to help us figure out what are the rest of our mutually incongruent solutions. We're going to find one of the 6. We're then going to use this number here, that 7, to help us find the other 5. Now, at this stage, once you have divided every number by your GCD, the whole goal of this is to multiply both sides here, so the 3x and the 5. The whole goal is to multiply each side by some number such that when you look at the left side, you'll get some whole number times x. You want to try to find a nice whole number that when you multiply that left side by, and you take the coefficient on the x mod 7, you get something that is ideally 1. If it's not that perfect case of 1, then it's just something smaller than what you started off with. So I started off with 3 here. I want to try to find some number such that when I multiply it by 3 and I take it mod 7, best case, I'll come up with 1. Only other case that I really want to worry with, I'll come up with 2. So what number can I multiply the 3 by and then take that number mod 7 to get ideally 1? Doesn't take too much thought. You don't have to go very high in the numbers to find that. If I take 3 and multiply it by 5, that gives me 15. Take the 15 mod 7, that gives me 1. And of course, what I do to one side, I have to do to the other to maintain the equality. So if we multiply both sides by 5, we get 15x is congruent to 25 mod 7. But notice that both of these numbers are larger than 7, so we're going to reduce these guys. Well, 25, if you take that mod 7, pull all the 7s you can out of 25, and you're left over with 4. So the 25 is congruent to 4. The 15x, you can think of this as the 14 plus 1 times x, or the 14x plus the x. The 14 times x, whatever the x value is, you have a factor of 7 in there. So you're going to pull out a nice whole number of 7s, and you'll get nothing left over. So when you take the 14x piece mod 7, that's just going to get wiped out. And that will turn to 0, and then the x just remains the x. So this is why we say we have x is congruent to 4 mod 7. So we've solved for one of our 6 x values. We found one solution, which is 4. Now, how do we find the other 5? I said take that value of 7, keep that guy in mind. Note that. We know we need to come up with 5 more. I'm going to add 7 onto a previously found and known solution to come up with another one of my mutually incongruent solutions. So if I take 4 and I add 7, I get 11. If I add 7 onto that, I get 18. Add another 7, I get 25. Add another 7, I get 32. Add another 7, I get 39. that's the first solution there that we found. And no, we have 1, 2, 3, 4, 5, 6. If we added 7 once again, just to show you, if I did 39 plus 7, that would get me 46, but 46 mod 42 is congruent to the 4. So this is why we stop at 4, 11, 18, 25, 32, and 39. Those are all of our mutually incongruent solutions to this particular linear congruence. And you can verify each of these. You could take each of 4, 11, 18, 25, 32, and 39, substitute each of those guys in for x in the original equation, and you would find that the congruence does indeed hold. So for this method, you divide by the GCD, use your congruence properties to solve the simplified congruence, and then add multiples of n divided by the GCD to obtain all of your mutually incongruent solutions. And just as a little bit of a warning, misuse of the congruence properties can lead you to a wrong answer when trying to solve these guys. But if you just stick with that process of check that you have integer solutions, and if you do, you'll see how many. Divide every number by your GCD, solve your simplified linear congruence. You come up with one integer solution, then add multiples of n divided by the GCD onto that previously known solution to come up with your next mutually incongruent solution. If you follow that process, you will come to the correct answer, and you'll come to it really quickly. The Euclidean algorithm is a more concrete and maybe a method that you're more comfortable with, but it is more time consuming. In the next video, we're going to do a few more practice problems. We're going to solve a few more linear congruences, so you'll get more comfortable, you'll get more practice with using this method. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.